overdue. Finally, 3 streams ago, since this was put in Notion, Matt's updated the skills multiple times. Yeah, you guys have wanted to get my honest thoughts on these skills for a while. But in order to do that, I had to use them. So I did. Over the last week, I installed a bunch of the skills from Matt Pocock's skills repo, which is full of gems that are worth talking about, from his process to the actual skills themselves. If I only covered Matt's reference point to learn and build your skills as you craft your own code bases, then you're a good engineer. The same difference applies here. If you just blindly copy my exact setup, it's like paying a bunch of money for a code template. It's cringe and bad, and it means you suck at engineering, period. So don't just blindly install all the skills here. At the very least, start with a slightly better entry point. I see my chat realizing that Potato was one of the builders of the React compiler. She was one of the biggest contributors there. She's unbelievably talented. Yeah, pstack is going to be the underrated gem in this, and I think you guys will like it a lot. I want to start first with how I set this all up. I started with a prompt. I want to figure out which Potato pstack skills would map well to the work that I do. I want you to audit my usage across my main machines, which were this MacBook, Leftbook, and BB1. Compare my usage against the skills in pstack. Make a nice list ranking all of them by how well they fit me and how much they could benefit me. Pull history here first, then break up subagents to do auditing, Opus 5 for all. I had a bunch of Opus 5 to burn at the time, so that's why I was testing this. And I linked pstack. It then created this document for me where it pulled in all the skills and then ranked them based on how strong of a fit they were, as well as how beneficial they would be to my work, and then a little brief why. So it immediately called out the interrogate skill, blast radius, technical writing, arena, the prove it works skill, and a few others. I will say that this deep dive was inspired by one particular thing. It was the interest I had in the unslop skill, because I had seen Lauren posting some of the prose that her agents wrote. And I was like, oh, that looks significantly less cringe than I'm used to Claude writing. So I quickly grabbed this unslop skill, which is very, very simple. There's also some fun prompting details here in the descriptions Potato uses, because again, as I mentioned before in my markdown overhaul video, the description's role isn't to accurately describe everything the skill does, because it's just fucking markdown. The only point of the description is to trigger the skill when it should trigger. You should treat the description as the thing that gets the model to do this, rather than as an accurate description of everything the model can do with the skill. I see it kind of similar to a YouTube video effect and fix. The first is in content puffery. So lots of these phrases: pivotal moment, testament, is not chat with AI in nicer windows. It is operating several autonomous developers without living in several terminal tabs. Prereqs are already settled. God, why is he using M dashes in his skills? Matt. Those fit your situation. There's grill with docs, as we talked about before. Triage, which helps move issues through a state machine of triage roles. Improve code-based architecture. This is one I actually wanted to try. A lot of these are self-referential, where the code-based architecture one will say to run the code-based design skill in order to get the vocabulary. Present candidates as an HTML report. Nice. As somebody who likes HTML skills, I like this a lot. Context MD vocabulary for the domain. Then it calls out grilling as well as domain modeling. Wayfinder's a fun one too for planning huge chunks of work. I also really like the separation in the docs between user invoked and model invoked, because these are very different. These are effectively plugins that you call when you want them yourself. Model invoked is more steering the model to do different things in different ways. And these ones are very useful. Like I mentioned before, the diagnosing bugs one has helped me a ton already. Wizard seems
Hey folks, today we're going to be covering networking essentials. This is part of our core concepts, which is basically material that we think you need either A, to put together a good design, or B, because your interviewer might ask you questions about in deep dives or in probes, and we want to give you all of the foundations for you to be successful in your system design interviews. Networking Essentials has about 4 sections. We're going to first cover the basics. We're going to cover the OSI model and talk about how networking works fundamentally. Then we're going to go into each of the layers, talking from IP all the way up to WebSockets, SSE, and gRPC, so you can be familiar with various protocols that are going to be important. We're going to talk a little bit about load balancing, because the intersection between networking and load balancing is really important. And finally, we're going to wrap things up with a bit of deep dives on regionalization, timeouts, retries, idempotency, cascading failures, practical things that you're going to need in your interviews. Let's get going. Networking is usually thought of as a layered cake, where at the top are application layer protocols like HTTP and WebSockets. And at the bottom are physical layer elements like wires in a network. When we're talking in system design interviews, we're usually only concerned with a few of these layers, but it's important that you understand these layers and how they operate. They're basically like abstractions. So recall that when you're building an app, you're probably not moving voltages around to write to a disk. You're probably using an open command and a write command. And that enables you to think about the important pieces, like what your data looks like, as opposed to the mechanics of the underlying hardware. Networking works in much the same way. These layers build upon one another and provide features and functionalities that you'll need. The first layer that we'll be concerned with in system design interviews is the network layer. This is where protocols like IP and InfiniBand live. The vast majority of applications outside of AI labs will use IP or Internet Protocol, and we're going to go talk about that in just a moment. At the transport layer, this is where you'll see protocols like TCP and UDP. They provide some additional functionality on top of IP. It becomes a little bit more clear if we work through an example. So when we want to make an HTTP request, we want to make a web server request to a website, we're actually going to transmit a lot of different information between client and server. As an example, when the TCP connection is initially established, we're going to use what's called a three-way handshake. There's going to be a synchronize, an acknowledgement of that synchronization, an acknowledgement of that acknowledgement. And then, and only then, is our connection established. After that, we can go and submit requests over that connection or that TCP stream. And then we're going to get responses back from the client. What you can see here is that these layers are building on one another. The HTTP layer depends on the TCP layer or the TCP connection being established. And the TCP layer assumes that it can depend on using IP addresses to route packets through the network. So the central idea here is that these layers help each other, and they also are oblivious to some of the details of the protocols that live below them. There's two important things about this for system design. interviews. The first is that there is a lot of back and forth, and that means latency when we're setting up and initializing connections. The second thing that's important is that there is state here. We have a connection established and a connection that's terminated. And that connection is not incredibly cheap for us to set up. There's actually a lot of latency in back and forth. And we'll need to be considerate of how we manage that state throughout the rest of our design. We'll get back to this in a bit. Let's go through each layer of the cake and talk about the protocols that occupy it and also what it does. We're going to start with the lowest layer, the network layer at layer 3. And at this layer is Internet Protocol, or IP. The responsibility for IP is basically to give names that are usable to nodes on the network and allow routing. We have two types of names, IPv4 addresses, which are 4 bytes. You can see this in this notation. And IPv6 addresses, which are 16 bytes. They're actually arranged in 2-byte pairs. The main difference for these is that we've run out of IPv4 addresses, and we haven't out of IPv6. You'll typically use IPv4 externally because it's going to be more compatible, and then IPv6 internally because it's more modern. IP addresses come in 2 forms, public addresses and private addresses. Public addresses are known to the world. They're assigned by a central body and routers are aware of them. So as an example, this is the range of addresses that Apple owns. All addresses that start with 18, this notation means the first 8 bits of the address are meaningful. That is the first byte or that 18. All of the addresses that start with 18 belong to Apple. And so what that means for routing infrastructure on the internet is if you see an IP address with 18, you can send it over to the routers that Apple owns. With private IP addresses, you can assign your nodes any name you want. The only important thing here is that you remember where they are and that your routers are aware of them. So an example of a private IP address is 192.168.0.1. It's probably the address of your home router. This is actually a special range, this 192.168. You'll see 16, so the first 2 bytes. That's allocated for local networks. And the whole point is to eliminate any overlap between private addresses and public addresses. What you don't want to do is give your toaster an IP address that also is used by Google. And then when you want to go and send a packet over to Google, it actually goes to your toaster. For system design interviews, you're going to see these public and private addresses in 2 places. Public addresses are usually used for your API gateway, for load balancers, for externally facing components of your design. And the key thing here is that people in the outside world need to be able to send them information. Private IP addresses are going to be used for everything else, all of your microservices, any other internal hosts. And you need to both allocate them and be aware of them. So if you're going to load balance between IP addresses, you've got to keep track of which host exists, where they are, and which ones you want to use. The next layer of our cake is layer 4, or the transport layer. With IP addresses in hand, I can send big packets or like a block of binary data to a host. But I'm usually missing 2 things. One is context. I oftentimes care about what application it's both destined for and came from. This is usually solved with ports. Also, I care about the ordering of packets and whether or not they were delivered. And these functionalities aren't provided by IP natively, but they are provided by some transport protocols. There's really three protocols that are in widespread use today: TCP, UDP, and QUIC. QUIC is a more modern substitute for TCP. It's increasingly being used for web traffic, and it has a lot higher performance, but it looks very similar in terms of functionality. So I'm going to ignore it for a minute to focus primarily on TCP and UDP. TCP is the default. If you're talking about system design, your interviewer is generally going to assume you're talking about TCP, because as application developers, you're usually relying on TCP for most of your communications. So let's talk about TCP first and some of the guarantees that it offers before we go into UDP and where you might want to break out of that default. So TCP is going to give you some additional features on top of IP, like guaranteed delivery and ordering. The way that this works is when you initially establish a TCP connection or stream, you're basically saying, I've got a sequence, and you're going to be giving packets a sequence number. Then, as packets go across the network, if they get out of order or they're lost, both the sender and the recipient will know what happened in between. They've got the numbers to back it up. So if you had packets 1 and 3, you might be able to assume that 2 was missing, and you could go back to the transmitting server and say, I lost 2. Also, if you got 5 after you had just gotten 3, you're going to wait a second for 4 before you emit 5 to your application. That's functionally how TCP works. Now, TCP is awesome, and it's the default because it's reliable. The hardest part about networking is that if the network fails to transmit or things are lost in the transmission process, it can be hard to deal with failures. And TCP mitigates many of those failures. But note that while I can guarantee delivery in one sense, like I'll know whether a packet was actually received by the other host, I can't really guarantee delivery in an absolute sense at just the network level. This isn't going to tell me, for instance, if the data was written to disk. It's not really relevant for things like CAP theorem, but it is relevant from a practical standpoint about giving you an insight into what actually happened on the other end of the network. Now, while all these guarantees that TCP offers are amazing, they have cost, and their primary cost is in throughput and in latency. If, for instance, a packet is lost in transmission, TCP needs to retransmit it before it can continue. And if your two hosts are very far apart, that retransmission can take up a lot of time. There are going to be applications where you don't need those guarantees and you want higher performance. That's where UDP comes in. You can think of UDP like a machine gun. It's basically spray and pray. As a sender, you're going to write your data, you're going to wish it, a good voyage, and you're going to send it off across the ocean and hope it makes it there. And in most cases it will, and in some cases it won't. Now, that kind of seems like it sucks and it kind of seems like wishful thinking, but it actually turns out to be really useful in some applications. As an example, when you are doing video conferencing, you don't want to, if you drop a frame, to go back to the host and say, hey, give me that frame again. What you'll usually do is just drop that frame out of the view, you might stabilize the audio a bit, and you'll keep going. That's not to say that you won't go back to the sender at any point and send them a message to say, hey, you're dropping the connection. Can you lower the transmission rate? But it is to say that you don't care as much about those individual packets. So UDP is going to be really useful for real-time applications or for lossy applications, multiplayer games, audio and video conferencing, sometimes live stream. In system design interviews, you may be forced to choose between TCP and UDP, and your default should definitely be TCP. The cases where you're going to want to use UDP are those where latency is paramount, and you can handle those failure modes where a packet is missing or you get things out of order. If those two things hold, then moving to a UDP-oriented service can be really useful. Now, note that UDP isn't supported by browsers natively. So if you have any browser applications, you're going to need to figure out a TCP version to use alongside whatever UDP applications like a mobile app might be using your service. Now that we've covered layer 3 and layer 4, TCP, UDP, and IP, we can graduate ourselves to layer 7, the application layer, where we'll be spending the majority of our time. The first protocol at the application layer is HTTP, Hypertext Transfer Protocol, and it is the most popular protocol for a lot of applications. And it's not just websites. Even RPC or remote procedure call applications will use HTTP because it's very versatile and it's battle tested over decades. The way that HTTP works is simple text formatted requests and responses. A request looks like this: get/post/1. I'm going to tell it which version of HTTP. And then I'm going to send it some headers alongside my request. This
drawing
get is actually called the method.
I love coming home to a clean floor. This Xiaomi robot vacuum handles dust. I feel its anti-tangle technology really works. It navigates around furniture perfectly.
The headers
Get yours
are
today.
a key value dictionary, and they can really contain almost anything. The HTTP standard has a bunch of headers that are widely accepted, like content encoding or accept encoding, but you're also free to define your own headers that you can use at will in your application. The HTTP response is going to include both the actual data that we want to transmit, but also a status code, which tells me was it successful or not, and some headers, which might indicate what format the data is in or the date that it was retrieved.
One of the more important
ideas behind HTTP is called content negotiation. When I make a request, I might tell the web server that I'm requesting it from what kind of things I can receive. I can accept compressed content, or I can accept certain encodings. Then
This drying rack is perfect for our HDB flats. It saves so much space.
in the response, the server's free to tell me what it actually gave me. I gave you compressed content, or you asked for compressed content, but I don't have it. I'm going to give you plain text content. This makes HTTP both backwards and forwards compatible. When new versions and new functionality are rolled out, new headers are introduced, and then servers and clients are able to negotiate what they want to use and what they don't want to use. The name Hypertext Transport Protocol might be a little bit misleading because it kind of makes the assumption that we're just retrieving web pages. But HTTP is much broader than that, and it can be used for building APIs, as an example. The most common way to build APIs on top of HTTP is using what's called REST, or Representational State Transfer. The way that REST works is two pieces. One, we're going to use those HTTP methods or verbs to describe what operations we're doing. Are we reading data? Are we writing data? Are we updating data? And secondly, we're going to focus on resources. And those resources are going to have URLs associated with them. So as an example, if I want to read user ID 1, I'm going to use the HTTP GET verb. I'm going to pass in the URL /users/1. And then when I make that request, it is going to return a JSON result, which gives me all the details about that user. Similarly, if I want to update a user, I can use the put verb. And I'll make a put request to the same URL /user/1, and I'll pass in the body of my request what update I'd like to make. In this case, I'd like to replace that user with username John Doe and email johndoe@example.com. If I want to create a new user in REST, I'm going to issue a post. I don't know the ID yet, so I'm going to post to the root of that resource /users. And then I'm going to pass in the body the data that I want associated with that resource. So I want that resource to be created with Stefan May and Stefan@hellointerview.com. In REST, I can nest these resources if I want to. So if a user has posts, as an example, then I can retrieve a list of those posts by sending a request to get/users/id/post. Basically, I'm organizing my API around URLs and around verbs. Now, this organization can be a little counterintuitive to some developers because they're used to thinking in terms of function calls. So it wouldn't be appropriate for a REST API, for instance, for me to have /update user as the URL. That wouldn't really make sense in REST. And the reason it wouldn't make sense is because update user isn't a resource, it's an action. Instead, what I would do is I would make this put call. There are operations that you might think of as mutations or operations that need to be performed. And typically in REST, what you'll do is make those an update. So for instance, if I wanted to start a game that already existed, I would go and make a patch call that would update the status of the game to running from stopped or from pending users start. And what that's doing is it's basically changing my thinking from making operations to making updates to resources. REST is very popular, and it is, in some sense, the default that we would suggest for how you build APIs in system design. There is some overhead, and there's certainly some thinking that you're going to have to do in order to make this work, but it has wide generality. Everybody knows REST and is able to use it, and it's reasonably performant for most applications. Now, just like there were situations where we might want to move from the default of TCP to UDP for special applications, there are certainly instances where we might actually want to use a different protocol for our application layer. One example of this is GraphQL. In GraphQL, we're going to acknowledge some of the problems that exist with RESTful APIs and then provide an alternative for them. Let's pretend that we are designing a mobile app, and we've got this view that shows some profile information, some status information, and a list of groups that this user is associated with. Whenever I open this page, in a RESTful context, I need to make 5 or more requests to the server. This is a bit of a pain. First of all, it means that my page or my screen is only going to be fully loaded as soon as all of these return. And secondly, all of the overhead of establishing an HTTP request and serializing the information happens in each of these requests. This would be an example of something that we would call underfetching, where basically I'm not getting enough information in the response and I've got to go and make other requests. Similarly, I might try to solve this problem by basically creating a kitchen sink endpoint. So this wouldn't be a valid RESTful endpoint, but let's pretend I have a /everything you might need endpoint, and it's going to return my entire database of information. I've solved the problem of underfetching. Now I only need to make one request, but I've created this new problem in that this request is going to be really expensive to return, and it's going to take a long time. There's going to be a bunch of latency. And so GraphQL is really trying to solve this problem that very frequently happens when we're developing apps or web pages, where our requirements are constantly changing. We might want to add a widget here or change fields here. And we don't necessarily want to have to change our APIs on the back end every time that happens. It's mostly a front-end concern. So what can we do? The way that GraphQL works is it basically provides a way for the front end to describe the shape of data that it needs to retrieve. And then the back end is then able to figure out where to get that data so that it can return it in the way the front end needs. This might be a little small on your screen, but this is a GraphQL query that says get users with profiles and groups. We have the user's ID and username. Underneath their profile, we have their avatar and their full name. And then we're also, in each of their groups, we're going to have a name, description, category. And so our GraphQL response is going to return all of this data and nothing more. What GraphQL has done is instead of telling me about resources, I'm telling it exactly the view I want to materialize on the front end. And then the back end is free to figure out what details it needs in order to make this happen. Now, GraphQL in practice can be very useful. And it's really useful in those situations where A, your front end is changing all the time. You're doing experiments, the requirements aren't firm. Or B, when you've got lots of different teams, maybe your front end and back end team aren't connected. Maybe your front end team needs to connect to multiple back end teams and they don't have the same API that they're using to expose their data. But both those situations actually don't happen as often in system design interviews. In a lot of cases in system design interviews, you're the sole author of your system, and the requirements are going to be fixed at the start of the interview. So GraphQL is really useful in system design interviews in those cases where either A, your interviewer is not giving you all the requirements or somehow implying that they're going to be changing quickly, or B, you want to be able to design a system that specifically can support these arbitrary query patterns. Sometimes we'll see GraphQL used, for instance, as the endpoint for newsfeed style applications, where it's not always obvious all of the different views that the client may need to request up front. And we want to provide some flexibility for the front end and back end to negotiate those two pieces. Another example of a protocol where we might want to move away from REST would be gRPC or Google RPC. The way gRPC works, it's built on top of protobufs. If you're not familiar with protobufs, they're pretty simple. They provide a schema. It looks like a struct if you've written C or C++. And that schema provides a way to serialize objects into very efficient binary representations. So this JSON blob is 40 bytes and it contains John Doe and his ID. But in a protobuf representation, it's only 15 bytes, which is a massive savings. If my server is handling gigabytes of data, then I only have to use half of them. gRPC builds on top of protobufs to add this notion of services. I'm going to define a message that is the request and the response. In my service, I give an RPC endpoint, get user. It takes in my request, and then it returns my response. In some cases, this is the type for my API. This will compile into stubs that can be used for a wide variety of languages, from Java and C++ to Node, Ruby, even some esoteric languages. What gRPC does is it makes the serialization and deserialization of my inputs much more efficient. Whereas with REST, I was using JSON blobs, which actually need to be parsed. With gRPC, I don't have a lot of that overhead. And that means that gRPC services can be up to 10 times as efficient, 10 times as fast, or 10 times as much throughput as their REST equivalents. gRPC also adds some additional features that are useful for operating microservices at scale, like client-side load balancing and streaming and some rudimentary authentication. So the idea behind gRPC is pretty sound. It's basically how Google builds services internally. The main problem with gRPC is twofold. One, mostly external clients don't support gRPC. Web browsers don't support gRPC natively. And secondly, operating with binaries in between services is really efficient and very effective for the servers, but it makes it harder for devs and other teams to be able to debug the information that is being passed over the wire. Now, of course, there are solutions for this, and I would love for gRPC to be used more widely, but the reality is it's not used that often. So what that means in practice for system design interviews is that gRPC is, in some sense, mostly useful for internal services. I might have a client who connects to a web server, an API server over HTTP or REST. And then when I have some high-performance bottlenecks on the back end, I can have my own controlled host communicate over gRPC. This is kind of the best of both worlds, where I get high-performance interconnects for all of these hosts, but I get a language and a way of communicating with my clients that's widely accepted and easily debugged externally. In general, for interviews, I wouldn't suggest bringing up gRPC unless you were tightly optimizing for performance. But in those cases, having a setup like this, where you've got a hybrid of REST and HTTP and gRPC internally, can be the best of both worlds. So far, we've mostly been talking about requests and responses, which is going to be the vast majority of applications that you're going to build. But there are a lot of applications where you want to be able to push data to your user as it's happening. Examples of this would be like stock ticker updates, or maybe notifications that you want to send to your users. And in those cases, you can just go poll the API to make repeated requests. But that means that your information is going to be delayed by up to your polling frequency. And there is some overhead of repeatedly opening and closing connections or making those requests. So enter server sent events, or SSE. SSE is an extension on HTTP. So it's basically an HTTP request, but with one notable difference. With a typical HTTP request, our response is going to be consumed almost wholly. That's not exactly true, because there's a lot of websites and web browsers which will process the request as it comes in. But in most cases for APIs, you can think that I'm not really going to be able to process the response until I get everything. So if I was sending a list of events where they happen over the course of 10 seconds, I'm not going to be able to process those events until all of them complete and then get sent in this response. With SSE, what I'm going to do is include additional headers in the response, like chunked encoding, and then opening and closing. And in those cases, you can just go poll the API to make repeated requests, but that means that your information is going to be delayed by up to your polling frequency. And there is some overhead of repeatedly opening and closing connections or making those requests. So enter server sent events, or SSE. SSE is an extension on HTTP. So it's basically an HTTP request, but with one notable difference. With a typical HTTP request, our response is going to be consumed almost wholly. That's not exactly true, because there's a lot of websites and web browsers which will process the request as it comes in. But in most cases for APIs, you can think that I'm not really going to be able to process the response until I get everything. So if I was sending a list of events where they happen over the course of 10 seconds, I'm not going to be able to process those events until all of them complete and then get sent in this response. With SSE, what I'm going to do is include additional headers in the response, like chunked encoding. And then in the response, I'm going to use new lines to designate how each of the events are happening. And so what will happen is when my first event comes, I'm going to pass it over the wire as part of the first line of that HTTP response. Because of the headers, all of the proxies and other things that are handling that request are going to send that response right onto my clients. And my clients are going to immediately start to parse the response. What that means is that I basically have a way to unidirectionally push notifications from server to client. And the nice part about SSE is I can use the existing HTTP machinery. I don't need new infra in order to build out on top of SSE. Now, the downside of SSE is that those connections are going to be severed frequently. HTTP requests are expected to return in somewhere on the order of 30 seconds to 1 minute. And so most routers and proxies are going to time out or disconnect requests that exist for longer than that. What SSE will do in those cases is automatically retry. Most of the clients, like event source, will open up a new SSE connection. And what they'll do is they'll pass the ID of the last event that it received, just in case one event happened between the time that it was disconnected and the time that you reconnected. But it's a bit of a kludge. You're basically existing on this connection that is constantly pushing responses, that is periodically severed and then re-enabled. That said, just because it's kludgy doesn't mean it doesn't work. And many applications can use SSE. It's a great option if you need to get updates to a UI for a short period of time. So as an example, if you're making a request or you're buying a product and you want to know the status, that might evolve over the next 15 seconds. It's also really useful for AI applications where you might want to stream tokens or responses back to the user because they take a while. It might take 30 seconds for your full response to actually be built out. So server-side events built on top of HTTP and allow you to have longer running requests that the server can push events down to the client. SSE can be super powerful for those push notifications, but in some instances, we actually need bidirectional communication. Our clients need to be pushing to the server in as much as the server needs to be pushing to the client, and we care a lot about latency. In those cases where we have high frequency updates and bidirectional communication, that's where we're going to bring in WebSockets. Now, I want to offer a caveat before I get into WebSockets that I oftentimes see candidates use these inappropriately. WebSockets are really powerful, but they also require a lot of infra. And it may be more appropriate to think about a polling-based solution or an SSE-based solution before you launch into to a full tilt WebSocket solution, especially if you shouldn't design WebSockets with this intention of having a lot of request and response style of operations, just because that's really not how WebSockets are designed. If you want that request response functionality, you're better off using HTTP. WebSockets in general are going to involve a lot of state for your application. If you've got a connection, a WebSocket connection, that means that connection needs to be active for as long as the life. The final protocol that we're going to talk about is WebRTC, and this is by far the most unique and the most niche protocol of the group. WebRTC, unlike all the other protocols, runs over UDP as opposed to TCP, and it's really used in those places where you either have collaborative editors or you have audio and video connections between clients. WebRTC is unique because it's a peer-to-peer connection. That WebRTC is a way for clients to connect with one another, which makes sense if you think about video conferencing or collaborative editors. The way that it works is pretty complicated, but let me give you just a flyby of the
Hey everyone, and welcome. OAI is a special CloudFront user that you associate with your distribution. You then update the S3 bucket policy to only allow access from this OAI. This prevents users from bypassing CloudFront and accessing the S3
Looking for a compact air fryer? This Tefal has easy control presets. I feel it's the perfect size for our HDB kitchens. And it is so easy to clean. It makes cooking healthier much easier. Dealing with constant humidity. I feel like a clean home shouldn't take all your time, dust and hair. It navigates around furniture perfectly. Enjoy a clean home effortlessly. I feel like a clean home shouldn't take all your time, dust and hair. It navigates around furniture perfectly. Enjoy a clean home effortlessly. If you want your product talked about in the most on-point way, this is the place lah. Just contact SG Lobang Shops, can already. If you want your product talked about in the most on-point way, this is the place lah. Just contact SG Lobang Shops, can already.
Guys, this new night juice and wow, guys, this coffee o gao gao croissant is really power, very gao.
Check out this ergonomic wireless mouse. It has a really comfortable design. It glides effortlessly across the desk. It features silent clicking for quiet focus. Upgrade your setup today.
Check out SG Creator Finds TikTok channel for more tech products, special deals, and limited time offers.
Keeping my home clean is so easy now. It handles dust and hair without tangling. I feel its suction power is really impressive. It moves around furniture completely on its own. Enjoy a clean home effortlessly.
This drying rack
You need to act fast. Grab this amazing offer on Pringles now before it's gone.
This GAN charger is a tech essential. Just plug in your laptop and phone. I feel this makes charging so simple. Power all your devices at once. Perfect for any desk setup. This GAN charger is a tech essential. Just plug in your laptop and phone. I feel this makes
Meet the all-new Samsung. Is your kitchen sink always a mess? This drain rack is a game changer. It keeps everything. Stop drinking warm water! Ugh, I hated that so much. This bottle shows the exact temperature. It keeps drinks ice cold for 24 hours. Seriously, get yours on TikTok Shop now. Want skin that glows all day long? This serum is my absolute holy grail. Run, don't walk to grab yours now.